Welcome back. We are going to solve one more problem regarding the free longitudinal vibrations in this video's lecture. So what is the problem he has given? That is, consider the system shown in figure. So there we can see here the figure is going to be, that is going to be spring 1, spring 2, the spring 3. They are given the mass 4 and 5, they are attached at the ground. So 1, 2, 3 are in the series condition and the 4 and 5 are in the parallel conditions, and these are going to be, again we need to convert it into the equivalent stiffness constant so that we can calculate the mass, frequency or mass of the particular system. So next, what else he has given in this one? The K1, K2, K3 and K4 and K5, the stiffness values of all these springs they have provided. Then find the mass m if the system has the natural frequency of 10 Hz. In this case, he has given the natural frequency of the system, but we need to calculate the mass of the system. So that we are going to be, again, we have to create the equivalent stiffness constants of these 5 springs, and then we need to substitute in that equation. As we know that the natural frequency Fn is equal to, what is the formula we do have? It is going to be 1 by 2 pi square root of Ke by m is there. In this case, Ke we need to derive from these springs and Fn is going to be 10 Hz are given. Right? From this one, now we are going to be solving the Ke and then we are going to be calculating the mass of the system. So then 1, 2, 3 are in the combination. Right? As we know that in the series condition, the solution is going to be like this. The equivalent stiffness of these springs in the series condition, 1 by K equivalent 1 to 3. That means 3 springs are there. That's going to be 1 by K1 plus 1 by K2 plus 1 by K2. So right, and in this case we do have the values of the K1, K2, K3. So if I am going to substitute in this equation, that's going to be 1 by 2 plus 1 by 1.5 plus 1 by 3. So from this, what is the final simplification from we are going to be getting here? That's going to be 1.499 Newton per mm we are going to be getting here. Right? That is going to be 1 by K. And if you want to suppose to calculate 1 equivalent, that's equal to 1 divided by 1.499, that is equal to 0.667 Newton per mm, you will get it. This is the value we are going to be getting the K equivalent. Similarly, 4 and 5 is in the parallel condition. So we need to calculate the equivalent stiffness for that also. So that's going to be K equivalent 4, 5, that is equal to K4 plus K5. What is the K4 value? That is the 1.5 and K5 also 1.5. If I am going to substitute in this equation K4 plus K5, then I am going to be getting 3 Newton per mm. That is going to be K equivalent 4, 5. So these 3 springs equivalent stiffness we got it. These 2 springs equivalent stiffness we got it. So then once it is going to be converted into equivalent to 1 spring and 1 spring. So it is going to be very clear that when the mass is going to be started to oscillating from its main position, the one spring is going to be started elongating, another spring is going to be, compression is going to be taking place. So in this case what will happen? So again the deflection is going to be the same in the above the springs and below springs of the mass. So then I am going to be taking the equivalent stiffness of these springs Ke 1 to 5, that is equal to the Ke 1 to 3 plus Ke 4, 5. Right? So then finally what I am going to be getting here, the 4, 5 is going to be 3 Newton per mm, and K 1 to 3 is equal to 0.67 Newton per mm. That is equal to here what I am going to be getting 3.66 Newton per mm. I am getting Ke 1 to 5. Now it is clear, this is available in Newton per mm. So this is available in Newton per mm. That's we need to convert it into the meters. Then what happened? I am going to be multiply with the 1000 in the next one. So we got that one. So then once I am going to be substituting this equation, Fn is equal to, what is the Fn is equal to? Already we have 10 edges, 1 by 2 pi square root of Ke is equal to, what's the value? 3.66 into Newton per mm. That's I need to convert into the meters. Then 3.66 into 1000, then it is going to be converted into this. So finally we need to calculate the mass of the system. So how we are going to getting mass of the system, that is equal to 10. So then what happened, this 2 pi I am going to be taking to the right side, the left side of the system. So that's going to be 10 into 2 pi whole square. That's going to be 3660 Newton per meter. And finally from this one, m is equal to, what's the value we are going to be getting? So that's going to be 0.927 kgs we will get it. So this is the mass, and here that is equal to 0.927 kgs. This is the mass. When the mass is 0.297, then the system is going to be making the natural frequency is going to be 10 Hz. In this way, we are going to be solving first 1, 2, 3 at series condition, 4, 5 is in the parallel condition. So then equivalents are going to be of these 3 springs and 2 springs are going to be, again we are considering is in the parallel conditions, because the deflection is going to be making the same deflection. One is elongation, one is the contraction. On this basis, we are going to be taking that again in the parallel condition. So we calculated the equivalent stiffness of the constant 125 is equal to Ke13 plus Ke45. This way we solve this problem. I hope you will understand this one. Thank you.